My warm thanks to Chris, who first nobbled me to come here, and for everybody else, and to the Institute, which has really looked after me and Pat while we've been here. So thank you very much, and I hope what I've got to talk about over the next 50 minutes or so will be of some interest to the people in the room. I think the title is basically self-explanatory. I'm going to be talking about linked data. I'm going to be talking about modeling. I'm going to be talking about issues that actually have been raised quite a bit already, but then when you prepare a paper, you're not quite sure what's going to be done before you get there. The other thing, of course, is the audience itself. And you don't know what audience you're sort of facing. So again, it may well be that some of this stuff is a little bit repetitive. I'm sorry about that. But I will try and... One of the things I'll be doing, I think, is I'm quite emphatically talking about linkage, and I'm quite emphatically talking about being outside the firewall. I'm a secondary analyst. I'm not inside the firewall. I don't have the data that can be used for linkage. I am someone sitting outside the firewall, and I have someone inside the firewall shove a piece of a database to me and said, this has been linked, go away and play. All right? And then the question is, how do I play? All right, and what happens? So that's what I'm going to be talking about. By the way, if you got your hand up and I don't see you, you can either stand up or you can yell at me, or I'm not sure. Maybe Peter. I may not see it, so I apologize in advance on that one. Okay, so I'm going to be talking about probabilistic record linkage, because that's the one that generates interesting statistical issues. We've already talked a lot about it, so this slide is, I think, quite self-explanatory. The applications of it, we've already talked. Becca talked about deduplication. I'm going to be talking mainly about combining data from surveys and registers, because that's essentially the sort of applications I've seen people talk about where they want to do some, if you want to call it secondary analysis. Obviously, no common unique identifier, so use probabilistic record linkage methods. And of course, there are possible linkage errors. The link record contains data values. It was made up of data values from different population units. And as had already been noted this morning, you have the issue of attenuation of statistical relationships in the actual, that is correctly linked population, the real underlying population. And my focus is always on those relationships. I'm only interested in those. Just to illustrate, here's some data I'm going to be talking about a bit later, but I'll just show you which one of the simulations. These data sets, the colors there, this is obviously a simple XY plot, just a simple linear regression. The population of 1,500 units made up of 3 blocks. The first block is made up of 1,000 of the 1,500, the second is 300, and the third is 200. And the colors, the red is the third block, the green is the second block, and the blue is the first block. I apologize to colorblind. I think I suddenly realized, isn't it red and green together is a no-no? Sorry. Oh dear, I apologize. I really do. Well, okay, but I'll try and talk my way through it. Anyway, what you have on the left is the actual data. On the right, this is the registers. After you have done some linking, and there are 1,000 of those units are absolutely correctly linked, unique identifiers. The green group, there's 90% chance you get it right, and the red group, there's 70% chance you get it right. And you can see what's happening is you can see the variation increasing. You're looking at a much more spread out population when you look at the actual linked data compared with the true data on the left. Now, this is showing you what happens. I've taken a sample from the population. The perfectly linked data for the sample, which I don't have, all right? So I've got a sample of 50 units from each block. And again, the colors are indicative of the block you're in. On the left, you have the real data, and on the right, you have what you actually see in the data that are given to you. And the dotted line over there is what you would get if you fitted a standard least squares to the actual sample data you've got. compared with the red line, straight red line, which is the true relationship. Move on a little bit, slightly more complicated. You say, oh, those are very big blocks, you wouldn't, necessarily link within those blocks. Well, let's suppose you had much smaller blocks. In fact, here I have 30 blocks, each of size 50. Same structure, same linear relationships. The colors are same, indicative. The three groups of blocks now. The first 20 blocks have perfect linkage. The next 6 blocks have 90% correct linkage. And the final 4 blocks have 70% correct linkage. And again, this is for the 2 registers. On the left, you have the actual register values. On the right, you have the linked register values. We go to the sample now, and you can see the same sort of thing happening over here, the attenuation effect. On the right, you see what happens when you take your sample data now, and the attenuation is slightly worse than it was before with its sort of 3 big blocks. Now this is 30 smaller blocks. So this is an example of what would happen with simple XY data. It's been pointed out to me when I deal with people that, okay, this is fine, but what most people want to do is just simple averaging. So why don't we look at that? So this is what I call the X domains illustration. So I have 3 domains in my population, same population. I'm going back to the 3 big blocks. Probabilities of correct linkage are 1, 0.9, and 0.7. That shows you the distribution. There are the domains are defined by 3 values of x equal 1, x equal 2, x equals 3. You can see the proportion of the population in each of those domains by block, by linkage block. And you can see that they're not the same, so it varies by linkage block. And then the original register data, those are those 3 nice box plots on the left. And when you look at the probability link data, you do see a rather big problem with a lot of outliers generated by the linkage process. This is again sampling. On the left, you have essentially what your sample data should look like. And on the right, you have the sample data that you actually observe. Okay, so you can see that you have attenuation, and you also have basically the creation of false outliers in your data. Yes, Becca?
So I just have a clarification question. So you're assuming that you're handed the linked data?
Yes.
Do you have any idea how it was linked, or is that not known?
I'm not showing that to you at the moment. I'm not interested in that. I'm just showing you the effect. We'll go into now essentially ways of dealing with that.
Okay.
But I'm just showing you the effect here. It's attenuation and the creation of false outliers.
Okay. Because my question, I guess, was then how you deal with the outliers.
Yeah.
Yeah. Okay.
Basically, that's what we're going to end up doing.
Thanks, sir.
Okay. Any other questions? Okay. All right, so let's have a framework for the problem that we're willing to deal with. So we're going to focus on regression modeling. And I'm going to work with just 2 population registers. I'm going to talk about extending that to multi-linking right at the end. I'm going to have what I call the X register, the covariates of my model, and the Y register, which is the response variable in my model. I'm going to assume some sort of probabilistic linkage. Typically, it's Feleghi-Sunta. And so the linked data set I'm given contains Y and X, but the Y I see in my linked data set is not the actual Y in the population, as it were. It's a scrambled up version of it, and I call that Y star. Now, I'm also going to assume that it's too expensive. These are both registers are fairly large. It's too expensive to completely link both registers, so a non-informative sampling method is used to select a sample, say from one of the registers, say the X register, and you link that to records in the Y register. So you're given actually a subset of the full linked registers. All right, also assuming the identifiers used in the linking process have no errors. Okay, so identifiers in the Y and X registers which are used in the linking process and themselves don't have errors, which is usually a big assumption. All right, so I want to make clear all my assumptions here. So I'm going to assume both registers are 1-to-1 and complete. They cover the same population. Okay, both registers can be separately partitioned into what I call Q match blocks, so I'm just going to call them blocks. I'd like to emphasize, I think in common with one of the previous speakers, the blocks I'm talking about here aren't necessarily the blocks you'll be using if you're doing Felige-Sunter type linking. These are just blocks I'm creating for the purpose of modeling the linkage error. All right, so there are these match blocks. There are no errors in the block identifiers in each register. Records in different blocks can never be linked. I don't have to worry about linkage across blocks. And I'm going to use a subscript of Q just initially to denote quantity specific to the Qth block. I'm going to assume non-informative linkage, which I think is a reasonable assumption. So whatever linkage errors I generate, they're going to be independent of regression errors. And this is probably a reasonable assumption if my blocks are small enough. Okay, big assumption here, but necessary for what I'm going to try and do is I'm going to assume that sampling from X, then linking to Y, is stochastically equivalent to directly sampling from the linked registers. Anybody who's done any linking knows that that's not the case. Okay? So this is an assumption. It does make the analysis subsequent, though, quite straightforward. Okay, I mean one-to-one linkage. So all records are linkable in theory. Of course, in practice, there'll be non-linkable records. That always happens. So again, non-linkage is at random, given X, so missing links are ignorable. For linking samples to registers, missing links are then equivalent to non-sampling. So it's really, when you have missing links, you're dealing with a missing data problem. All right? And I'm also, and this is important for what I'm going to try to do, is that you've been given this linked data set, but the agency or the organization that did the linking may, in the goodness of its heart, also give you some summary information about the registers from which basically underlie the linking process. This may well be published data about those registers that you can dig out elsewhere. Okay? So you do have some extra information, auxiliary information. And in particular, the auxiliary information I'm going to assume is that block averages are available to you for both Y and X. All right, as I said earlier on, I'm taking a very strict secondary analysis perspective. So I have our link sample data plus the block averages. In order to analyze this, I'm going to have to set up some sort of what I call a linkage error model. I'm going to have to sort of characterize how the linkage errors have perturbed what I should have seen in the first place. All right, so that almost automatically, given I have one-to-one and complete linkage, leads me to a latent random permutation model. So essentially, I view the impact of linkage as effectively, or the linkage process as the creation of a permutation matrix which scrambles the indices of the real data and leads to what I actually am given over here, this vector here. So for example, in this one over here, the red indicates scrambled units, and the blue indicates units that are correct. The assumption that blocking is linking is blocking is block specific. I think that should be linking. Allows us to drop the Q subscript, so I'm going to get rid of that now. So all results from now on, you can think of them as aggregated over blocks. I've got to introduce a model for the linkage error process, the LEM. And one model I've been working with for some time now, first not entirely due to me, there are predecessors to it in the literature, is what I call the exchangeable linkage errors model, or the ELE. And it's a very simple model. It basically says within a block, everybody has the same probability of being correctly linked, and everybody has the same probability of being incorrectly linked. Okay, very, very simple model. Okay, so it's obviously unrealistic, but it helps us go a long way and comes up with something which you can then test against real life situations. Some of the consequences of that model is, if you look at, remember, the linkage process is this unobserved linkage permutation matrix A, is its expectation, given the covariates, is this T over here, and it's going to have just the same number lambda going down the diagonal, and you're going to have these etas all over the place elsewhere. Now, since linkage is one-to-one and complete, T is doubly stochastic. And so you can automatically see that eta must be a function of lambda. In fact, eta is 1 minus lambda over capital M minus 1, where M is the size of the block. Convenient to put delta equal to the difference between lambda and eta, and then you can write T as delta times an identity matrix plus eta times a matrix made up all of ones. Okay, now I'm going to take an aside. Okay, that's a sort of structure, if you want to call it, for the linkage process. Now I'm going to say, well, okay, I really want to actually integrate the auxiliary information I have with my linked data. And I'm going to try a maximum likelihood approach. And so I'm going to use something called the missing information principle, which I suspect most of you are aware of, but I'm going to say it anyway. Okay, it's the MIP, and it says maximum likelihood estimation equations, right, or score functions, are defined by replacing all sufficient statistics in the complete data MLE estimating equations by the conditional expectations given the observed data. Okay, that's a well-known result, been out there for a very long time. It's the basis for the well-known EM algorithm, and in fact I have a book with David Steele, Sujin Wang, and Alan Welch, which discuss the application of this sort of the MIP to the analysis of survey data. Okay, so that's how we're going to develop our MLE for this situation. Okay, we have sample data, so I'm going to assume that I can, at least notionally, partition this unobserved A matrix into a sample component and a non-sample component. By the way, although the A matrix is capital M by capital M, the sample component obviously will be little n by capital M. All right? So it's the first little n lines or rows of the A matrix. And similarly, T can be decomposed into TS and TR. The expected values under our model, our analysis model, so the expected value of y given x, which I don't see y, I'll write as little f. And so the sample values of that I'll write as little f sub s. So that's x sub s times beta. The ELE says that TS, this component, sample component up here, will be the expectation of that thing given x. And that will be of this structure here. Those of you who know R will recognize the C-bind, the column bind function. So it will be the column bind of this matrix here, delta times an identity matrix of order little n, plus eta times a little n by little n matrix of ones. And then you bind that with a eta times a non-square matrix of order 1s. This is 1s times 1r to the t, so that's a little n by m minus little n matrix of 1s. All right, now in earlier published research with colleague Gunki Kim, we developed the expectations, variances, and covariances of our linked data given this structure. These equations here show you what those look like. The only thing I would want to point out of these results over here is that, yes, they all depend on this T. This T turns out to be terribly important. It's basically equivalent to the, if you want to call it, the thing that characterizes the linkage process. It's in all the covariances and the variances. But the important thing is to realize that in the variance term, the sigma squared, which remember is my noise in my analysis model, occurs in this rather unusual way. So you have sigma squared out there, and this thing is a variance of ASF divided by sigma squared over here. So this is a nasty little thing over here, which you have to allow for in the analysis. And I'm just going to capture all of that in this cap sigma S over here. But remember, this cap sigma S over here is a complicated function of the sigma squared itself. Even though there's a sigma squared out here, there's also a sigma squared in there, and this variance of AS times F. All right, so a little bit of extra notation. Put little f bar equal to the sample averages of x times beta. Put C equal to this row matrix over here, which is a little capital T over there means transpose. And W, this cap sigma here, which involves those little sigma squareds in there and things like that. And outside there, things which, if you have any memory, or most of us don't, these are things to do with the covariances. Then you can easily show that the joint distribution of the thing you don't know, the thing you do observe, y star s, and the thing you do observe, which is the sample the population average of y, the conditional distribution of that given all the x values has this structure with this mean vector over here and a variance covariance matrix which involves this W over there. So under joint normality, we know what the distribution, the conditional distribution of the thing we don't know, given the stuff we do know is. And so the full information maximum likelihood estimating score function for beta essentially tells us to take the standard score function for beta for a linear regression, replace things which involve y, which we don't know, by the conditional expectation of y given the things we do know. And when you do that, this turns out to be the full information estimating score function for beta, which again involves this W, in fact the inverse of W. Right, under the ELE, nice thing about the ELE is it has nice symmetry properties. So you have these sort of nice relationships here. Okay, so this MT to minus 1 is because that's part of W. And over here, you can then restructure things, rewrite things a little bit, so you can actually express the full information maximum likelihood estimating function for beta as something that looks remarkably like a weighted standard estimating function. These x tildes over here are extended versions of x, and y tilde is an extended version of y. You can see what I've done is I've tacked on the population average of y to the actual linked y values, and I've done the similar thing with the population average of x's over here. And so if it wasn't for that W, it would be basically saying add on an extra terms, extra data value, which is your auxiliary information, to the linked data, and go away and use that. So under normality, an ELE then, my maximum likelihood estimator is my standard weighted MLE. But you can see the weights here are not diagonal weights, which is the standard assumption people make. This W matrix over here is a non-diagonal matrix. All right? So it's not something that is trivial to work with. And here we have W, and this shows you what the structure of that W matrix is. So ostensibly, it looked like it got a simple result, but actually inside that result is this rather messy expression here, which depends on sigma squared. Okay, what about the maximum likelihood estimation equation for sigma squared? Well, you can use the MIP as well over there. Take the conditional expectation of the quadratic product of the error terms under the model, and this is what you end up over here. Now, this involves the conditional expectation of the squares of the y's, some of the squares of the y's given the y stars. All right, you can derive what that conditional expectation looks like. It's a fairly well-known result in the literature, but just to make it look simple, I write A and B like this, and then you can write the conditional expectation of the squares of the y's as the A matrix, which is the conditional expectation of y, times A transpose T times A, plus sigma squared times the trace of this matrix B, which involves that W to the minus 1. Effectively, this is telling me that the loss of degrees of freedom, if you want to think of degrees of freedom over here, CT, W to the minus 1C, tells me basically how many degrees of freedom I've lost as a consequence of the linkage process. If I had perfectly linked data, that would be 0. I wouldn't have lost any degrees of freedom. Okay, so the full information maximum likelihood to estimate of sigma can therefore turns out to be slightly more complicated. It looks like a standard quadratic form, but it's weighted by this W to the minus 1. Okay, so W depends on sigma squared and the variance of AS times F. On the other hand, this CCT over here does not. All it does is depend on the linkage process. In particular, all it does is depend on T, which is, like, if you want to think about it, the characteristics, the thing that defines the properties of the linkage process. So it depends only on lambda. Okay, so once we've got lambda in this case, because the ELE says everything's defined by lambda, you can iteratively solve these things, and it works quite nicely. But the problem is, what is this W? Well, that essentially requires you to get the variance of AF And in 2009, I did some work which said that you can approximate this variance of 8f under an ELE by this nice expression here, which separates out the expected values, the f's, with the lambdas. That's under the ELE, you get a nice approximation. This is one of the advantages of the ELE model, is that it does lend itself to this sort of approximation. So you can use that approximation in the process as I put down there. Okay, next. Some special cases here. Suppose you have no linkage error. Okay, what's possible? Everything could be perfectly linked. Okay, well, actually, in the 2012 book, we actually considered this particular problem in chapter 8, and this obviously you get the same result we have in that book. Okay, so this just shows you how it all agrees with stuff we've had earlier on. The other thing would be if you have complete register linkage rather than linking a sample to a register, and then obviously you have a result where you still have obviously the W matrix turning up in the estimation of beta. The W matrix depends on sigma squared, and in this case, this sigma squared over here is effectively a quadratic form, but divided by an appropriate set of degrees of freedom. Okay, so that's one way of doing it. That's maximum likelihood. But that's not the only way you can do this thing. Lots of other ways you can tackle this problem. Earlier work, the stuff I've been doing with Gunki over the last 4 or 5 years now, probably longer, 6, 7 years. Okay, so this is Kim and Chambers 2012. I think that's 2012A. I should have put an A in there. Okay, so that didn't do maximum likelihood. That ignored the extra information you might have. And it just said, okay, let's suppose you've only got the link sample data. That's it. All you've got is that. And you then want to use an estimating equation to get your beta. Well, a sample-based unbiased estimating equation for beta is given by this H tilde S over here. Here's your link data. Here's the sample data, X's. And this is T tilde S is effectively the ELE. But remember, the TS was a non-square matrix. It was of order little n by capital M, the size of the block. I don't know the other elements of the block, so I have some, say, survey weights or something like that, and I have to estimate the contribution from the other parts of that block, the non-sample units. So that's what this T tilde is. It's like a weighted survey estimate of the unobserved TS. You can then get a beta hat from it, which involves G over here is an arbitrary estimating equation matrix. So whatever G you want to choose over here, you solve that, you get a beta hat. You can do a sandwich approximation to the variance. You can estimate sigma squared using a moment type unbiased estimator. You can work out that's expected value under the ELE of that is sigma squared. Okay, and so you can go ahead and do this sort of stuff. And we tested it out, and it works reasonably well. There are 3 standard choices. Actually, it turns out I'll show you an example where there's a 4th choice as well. It could be more. But certainly, you can choose G is just equal to X prime. Lahiri and Larson in their 2005 paper effectively used G as X prime times this T transpose. The most efficient choice of G, this comes out of standard sort of BLUP type arguments or BLUE type arguments, is the Lahiri-Larson weighting estimator, but then you multiply it by this sigma to the -1, which was this matrix I had earlier on, which involved the unknown variance components. So obviously you'd have to plug in, and it's like a heteroscedasticity problem where you plug in the estimated heteroscedastic parameters into your weight in your efficient weighting function. Okay, one of the things Gunki and I had looked at before I got onto the maximum likelihood was to just see if we can take the estimating equation approach with this extra information and just tag on an extra term, an extra calibration term to the estimating equation, which effectively allowed for the contribution from the fact that if someone tells you what the average value of y for the population is, you know the average value of y for the linked data, you can immediately work out by subtraction what the average value for the non-linked data of y is. Okay. So effectively, you add an extra term in here. Little g over here is a chosen weighting function. We tried a couple of weighting functions, Gunki like this one down here. I'm not going to go into too much detail about this, except this, I'm using this in some of the analyses just so you know where it's coming from. So there's effectively a methodology which uses estimating equations, which ignores auxiliary information. Here's one that uses estimating equations, adds in the auxiliary information by a calibration term. It's not maximum likelihood. So some simulations. Okay, so the data sets I showed you earlier on is the first set of simulations. So in that one, my intercept was equal to 1, my slope was equal to 3, sigma squared was 64. So that was simulated data I showed at the start. I had two scenarios, and these again were the ones I showed earlier on. The one where I had 3 large blocks, and scenario A, and scenario S was where I had the 30 smaller blocks. In both of them, I did simple random sampling without replacement within blocks. Both of in scenario A, there was 50 taken from each of those blocks. So obviously, it's not proportional sampling. In scenario S, I took 5 from each of those 30 blocks. All right. Linkage errors were generated using an ELE mechanism with lambda equal to 1 for the first block in scenario A. That's the biggest one. So no linkage errors. Then 0.9 and 0.7. Now, obviously, I need to know lambda in order to apply these techniques that I've been talking about. So how do you get lambda if you're outside, if you want to call it the firewall? Well, the simple answer is you can't. But maybe you can persuade someone inside the firewall to run an audit sample. And it doesn't have to be a very big one. So let's suppose they ran an audit sample which looked at 8 units on block 1, 8 units from block 2, and checked to see if they were right or wrong. Okay, after the linkage. So a total of 16. Okay, and then if I look at the X distribution, that varied between blocks, as you can see, which is, I think, clear from the where you saw where the colors were in the plots right at the start. Scenario S, similar sort of thing, but now I have 30 blocks. So lambda equal 1 from blocks 1 to block 20. Lambda equal 0.9 from block 21 to block 26. Lambda equal 0.7 from block 27 to block 30. Again, I'm going to allow for maybe an audit sample, but now I only take 2 from each of the blocks which have errors in them. So 2 each from blocks 21 to block 30. Total of 20. And again, you have the same X distribution, but now spread across the different blocks. Our simulations, we looked at lots of different things, but I'm only going to show you the ones that are highlighted here. So the first thing I'm going to show you is the sample weighted state estimator, the naive estimator, because remember, I took a non-proportional sample, so I have sample weights, so I would use that in a weighted regression. So it's a sample weighted estimator, ignores the linkage error, treats them as if they're absolutely, the linked data are fine. I have SBL over here. All right, that's the solution to a sample-based estimating equation, BL type weighting. That's what we found in the past is the most efficient type of weighting for this type of approach. Then I have SBLP, which is the same as SBL, except I've added a calibration term in there. And then finally, I have my maximum likelihood estimator over here, SML. Okay. I'm okay for time, I think. Yeah, that's what I thought. Yeah, it's all right. Okay, pictures. Here we are with the XY simulation, scenario A. The top line, actual value of lambda used in the analysis. So very kindly, they gave you the actual value of lambda. In bottom line, all you had was the estimate from the audit sample. So you could think of it in a way they had confidentialized the linkage errors information by giving you a linkage error plus a sampling error. Okay? You can think of it that way. So this, you can think of the top as non-confidentialized release of linkage error characteristics. Here, confidentialized release of linkage error characteristics. Okay. All right, so what we have each, that's the intercept, that's the slope coefficient, that's sigma squared. Those are the three things that are of interest to me in the analysis model. Okay, then we have our estimators. This is a simple weighted estimator. That's the estimating equation, which is bias corrected. That's the one with the calibration term in it, and that's the maximum likelihood. These are values over simulations. Similarly here, there, down, all around there. If we look first at the simple one, we can see automatically what's happening over here. You're getting attenuation. Attenuation is reducing the slope, increasing the intercept. What you'd expect. That is being corrected by all of the methods. But it's being corrected best by the ML. There, there, and there. And it's being corrected even if you're given data about the linkage process which has been effectively anonymized, because it's coming out of an audit sample with usually quite a large variance attached to it. Okay, scenario S, that was 3 large blocks. This is where we have 30 much smaller blocks. It doesn't change that much. We still see, obviously, the simple weighted solution is still not very good, as you'd expect, because it's ignoring linkage. The other one's correct. A little more difficult for them to correct, but the maximum likelihood is still almost spot on in every case. Spot on. And with the smallest variance. Okay, so that's linear XY simulations. Want to go to the domain, because I've been told that people don't do regression, they just do averages. So some of these, this is just showing you what happens if you have these 3 domains, X domains, and you would just want the average value of Y in each domain. Again, you have scenario A, 3 blocks, 3 large ones. This is the same table I had before, showing you how the population values are distributed by X in the different blocks, 3 large blocks. And scenario S is the same thing, except I have 30 blocks. Okay. So the focus now is on the average value over here for the X1s, the average value for the X2, and the average value for the X3. By the way, in theory, the average value for X1 in the population is 1, the average value for X2 in the population is 3, and the average value in the population for the X equals 3 is 5. Those are the true coefficients, the true averages. All right, now we have scenario A. Now, attenuation, remember when we were doing this before, we saw lots of outliers. Okay? So attenuation, yes, there is attenuation, but not in every coefficient. There is no attenuation in block 2, X equals 2. Remember, this thing over here is your sample, standard sample weighted estimator. In this case, a weighted average. There's no attenuation in 2. It's quite good, actually. But it's not so good in one way in block 1, or sorry, in category 1, and it goes the other way in category 3. So, yes, you might hit it in one of them, but you miss on the others. Maximum likelihood, oh, one of the things over here is this calibration thing goes haywire. Goes haywire. So just adding a calibration term, before we just had a simple XY, now it has a slightly different X structure. It's clearly quite sensitive to the X structure. Okay? So that's something to be worried about that approach. Okay, the maximum likelihood, bless its soul, hanging in there. Doing very, very well indeed. Okay. That's with scenario A. Here's scenario S. More woes as far as the other estimators are concerned. But again, bless its little maximum likelihood estimator. It's getting boring now. Okay, so I'll move on. Okay, now I work with James Chipperfield at the ABS, and he's recently developed slightly different tack on this. First of all, he notes, and this is basically taken out of his research note on this. Oops, I should maybe go that way. That most people, when they deal with linkage errors, confuse a matching error model with a linkage error model, an MEM with an LEM. They're not the same thing. One is a model for the probability of a match given your match blocking variables, your matching variables. The other one's the probability of a correct link given your covariates. Okay? So MEM is a model for that two records match. LEM is a model that a link record is correct. They aren't always the same thing. But a lot of people out there have treated them as the same thing, have used the MEM as a, if you want to call it, an alternative. If you don't know the LEM, someone's giving you the MEM, use that. The LEM is essentially the only model of interest to a secondary analyst. They don't care how you match things. Give me something which tells me what the properties of the linkage error are. All right. Now, the LEM corresponding to the ELE turns out to be convenient and with sufficient blocking in it, capable of representing many real-life linkage outcomes. In the same way that stratification models, because the ELE with blocking is just basically post-stratification. Stratification models and tree models are often good at approximating very complicated regression models. It works the same way. So, what James has done in his thing is say, well, I'm going to use the estimating equation approach, but my weighting matrix is going to involve x times t to the minus 1. Very carefully chose it that way. I said you could choose G any way you liked, and I gave you 3 options. This is a 4th option over here. The advantage of this one is it turns out, when you're looking at beta hat over there, you have your standard x prime x now. And all that happens is you have x prime times an imputed value of y. With the imputed value of y is just t to the minus 1 times your linked value. So provided you transform your linked values, by multiplying them by the inverse of this T matrix, you can just use standard results. Standard estimating equations. Of course, you still need to know this thing. So you still haven't got away from the problem, except there's a very simple solution, if someone gives you T. And you can actually convert that into a weighting solution. So you can have actually domain-specific weighting, like small area estimation weights. Okay? And that just uses the fact that the x's have a 0-1 structure when you have domains. All right, you can use the ELE bootstrap, which is based on the ELE, to estimate t to the minus 1 if you are the primary data linker, so you have access to the matching process. All right, then release domain-specific weights w and or adjusted y hats. You can also use a parametric bootstrap to calculate standard errors. And it's worked quite well in stuff that James has done. Okay. All of this is nice. The main thing, of course, is you end up with something that this G matrix here generates unbiased results. But as we know, it's not going to be efficient. But at least it's unbiased. And it's very easy to do. All right. I also have some results on logistic regression, just to show you that all of this works through for logistic. At this stage, I think it's probably better to have discussion going than rather going to but you can apply this to logistic. And there are some results for the logistic simulation results, which indicate basically the maximum likelihood works quite well there as well. Okay, some comments based on limited simulation experience so far. There are for and against. If you use MLEs that combine linked sample data with auxiliary population data, then you can certainly perform significantly better than matrix-weighted estimators based on linked sample data. That extra information coming in from those auxiliary calibration information is very important. Against, you've actually got to require some sort of model for the linkage error process. All right, so you do have to do it. You do have to be able to somehow get hold of what's driving the linkage error process. You also require non-linkage to be at random within a block. That, if the block size isn't too big, that's not such a big assumption. It does require non-informative linkage. Probably a reasonable assumption, but people could argue with that. What are the next steps? I think we were told in our discussion, this is something I've read, is what are the open issues here? This is not a closed problem. It's only just the very start. Are there other useful models for data linkage errors for a secondary analyst? All right. Mislinks are easy to include in this model. In fact, this is what we've done. We had a paper in CSDA on that. Dealing with informative mislinks is difficult, as dealing with informative non-response is difficult. There's no difference. Overlapping registers can be dealt with in this framework, but it tends to get a bit messy, particularly in notation. We can also drop the one-to-one linkage assumption, but again, you basically lose that nice stochastic permutation structure. You can extend, in fact, we have extended to multiply linked register, or multiple registers, or linkage of multiple, or we call multi-linking. In fact, this was given in the 2012 B paper and also in 2015, it's a note and stat. We dealt there with 3 registers, but you can extend it logically to as many as you like. It allows for correlated linkage errors. So you can link x1 to y, link x1 to x2, and the linkage errors across those 2 linkage processes can be correlated. The maximum likelihood theory for the multi-link registers has been sketched out, but we haven't yet carried out the empirical performance. There is a connection here to multi-linked inference. There's some discussion of it in Harvey's work in the book he had with the Harron, Goldstein, and Dibben book. Something that sort of became fairly clear to me, the privacy issues with linkage error models and releasing information about them. We need to think about the block definition for an ELE. The smaller the block, the more problems we might have with privacy. Not sure whether releasing lambda would breach confidentiality or not. If you're using an ELE model, everything is driven by this lambda coefficient. That might be viewed as confidential. On the other hand, maybe adding random noise to lambda, as we've done effectively with our audit sample, might be quite acceptable and still works. So that's something to think about. We looked at very simple models. Obviously, you want to do more complex stuff. A student of mine, Clarung Samat, and I looked at the extension to Remel type fitting for 2-level models. It works. But obviously many other more interesting applications need to be explored. And what we're sort of completely ignoring here, of course, is when people start use these data, they don't just fit some sort of preordained model. They go through a model selection process. I have no idea how you build all this stuff into a model selection process. So, interesting problem. Real data applications. Well, the ABS, James, who works at the ABS, has applied these ideas to their linked data, demonstrated they work, but nothing else so far. So again, no real big applications sitting out there at the moment. And of course, software. Software, software, software. Without software, you are nowhere. So I think that's a really important consideration. Secondary users are going to, first thing to say is, what package can I use? I said, write your own R code. Ooh, no. I'd rather live with the bias. Okay, fair enough. Some references over here. Hopefully in the appropriate format. So, and that's it. Thank you very much.
Okay, thank you very much, Ray.
Yes.
I probably missed it. Can you just clarify again the difference between the approaches that you were discussing and Chipperfield's approach? Where
he basically is using one of the simple approaches I initially discussed, using the estimation equation approach, but his weighting function, the G function, is a very simple form of G function.
X times the error.
X times the inverse of the expected.
Isn't that similar to Lahiri-Larson?
No, I'll show you what Lahiri-Larson looks like. Sorry, I have to do this a slow way, but it's there. Lahiri-Larson, they have X times the transpose, not the inverse. It's not the same thing.
Inverse in the Chipperfield.
Inverse in
Weighting,
it's the inverse in the Chipperfield. So Lahiri-Larson is the transpose. At this stage, we have not compared, but the advantage of the t to the minus 1 is that means effectively you can write this thing as essentially standard linear regression involving imputed values.
If you wanted to use this in practice, how would you define your x's? Because you'd have to have a different x for every analysis you did, and you need to get that information from
The x's are the covariates. the model you're building. I haven't said how you got to the x's, that's the model selection process. So that's a really important problem.
Given that,
Given your x's,
then got to go and ask.
you got to get the y to go with those x's, yes.
But
Someone's got to give you that.
You've also got to get your lambdas for your different blocks.
Oh, that's really fundamental.
So how would you ever imagine getting that in reality?
Well, James seems to be quite okay with the idea of releasing these, in his terms, the y hats.
All right. So you can then reconstruct.
Yeah, you would, and then you just use the y hats. All right. So he's quite comfortable with that. I'm just pointing out that the T is a big matrix, but it just depends on the lambda, right? So all you have to do is release lambda. You don't like it, like release Wadja. So you send out a fuzzed up version of lambda. It works. Worked for us.
So basically from a small audit sample. Would you really
You don't have to. You can just fuzz it. I don't have to do an audit sample. I know lambda. I'm the linker.
everything's sort of based on these assumptions, you know, that you laid out.
Yes.
So,
So obviously,
changeable, error,
all of these you're going to have to go and break and check.
and you don't know. So basically, all you need is a diagonal, because the rest is just.
Yeah, everything else is just defined by that lambda. Then you just release that fuzzed up in some appropriate way, and that's it.
And some of the approaches that Harvey was doing in terms of imputation, you know, comparing the imputation as this sort of been.
I don't know the link at this stage. I really don't know. It's obviously very interesting. There's 6 months of this program still to go. Obviously, people here who might take it upon themselves to check this out. So, yes, it's just out there. Interesting set of problems. If you are going to analyze linked data as a secondary analyst, and I keep coming back to that, as a secondary analyst, outside the firewall, you can't sort of bring things together. You're not in this wonderful big data situation. Yes?
But the sample size increases. How fast can your blocks grow, the size of the blocks?
I have no idea.
So you didn't look at that.
Asymptotics, asymptosia. I don't have a passport for asymptosia yet. So I have no idea.
And those parameters, lambda, and so can they be dependent? So can they depend on the block? So they don't have to be the same.
Oh, well, you can see they did depend on the block. In my
Okay.
simulations, they change from block to block. Oh, no. They have to. That's the whole point of them. They are block dependent. So this is the confidentiality issue. The more blocks you have, the better you are, the more reasonable the ESLE model is. But then the more lambdas you have to release, the more the issue with confidentiality. This trade-off again.
So and they can depend on the sample, so they don't have to be constant.
Mm. Yes.
So if I have two different specifications for the regression model that I want to run, so forget about model building, model search, whatever, I just have two and I want to compare. Do I need two different lambdas for each of those?
No, the lambda goes with the linkage process. So let's suppose you have two x's. Let's suppose you have an x database and a y
It's
database.
conditional on X, right?
Yeah, I know, but conditional on the whole x. All the x's.
So I could just take a saturated X.
Yeah, saturated x and
follow
condition.
using
Yeah,
big lambda.
yeah. Because basically that's just saying all the betas are 0.
Questions? You've got a few more minutes. One very quick question I've got. So you mentioned the ABS been using this. And you also mentioned software. So
Well, no, they have their own. I
Have
mean,
their own, so-
Chipperfield's doing it.
what's the size of the data they've been using? These
Well, James has just done some simulations with 100,000 units in it, replicating Filigi Sunta with that. But they've gone up. They've used it for their census. They have a census longitudinal sample. I don't know what's that, 2%, 3%? Anyway, it's big. It's a big one. They've applied it there as well. Yes.
So I actually have to teach this.
Really?
Yeah. And of course I you know, sort of talk a lot about the exchangeable model and the error
Yeah.
rates model. But and of course I tell them about the audit samples and what they need to do. But you mentioned this
But by the way, this is
other
the,
approach with,
this is the
after
first
you-
I heard, Natalie, this is the first I heard anybody's teaching this
I am
stuff.
teaching it.
I'm honored, thank you.
But the parameters that come from the linkage, the match probabilities, I've seen papers that use that, and
Lahiri and
it
Larson
doesn't
did.
make any sense. You need to.
That's what I'm saying. The MEM
So
is
why
not the
is
LEM.
that? So have you seen papers that people have been using those?
Well, no,
A little bit that Harvey used them in some, to inform
Excuse me.
priors for the
I know.
imputation, but
I thought I'd put this up. This is actually James's research note, which was presented at the ABS Methodology Committee meeting this week, as we speak. Lahiri and Larson and Hoff and Zwinderman estimate Q. His Q is my T, using the posterior probabilities of a match. That's the MEM. We often found, results not provided, in the simulation study that he reports, which is the big one, that the inverse of their estimate of Q, using these MEM techniques, either did not exist or was unstable.
right. So it's
So it said further research into resolving this issue would be worthwhile. I quite agree.
Just it's more just a comment, a connection. So, Zhao Meng has this sort of multi-phase inference thing. I don't know if you've heard this, but it's this recognition that most data that we get goes through several phases of preparation or analysis before we ultimately analyze it. So, in some sense, when we get a data set from an agency, we're not really learning about data in the state of nature. We're learning about data that have been filtered through the agency's edits and imputations and recodings and confidentiality procedures and whatever else. And he doesn't have any solutions for it other than just start pointing out the problem and
Yes.
for one particular issue of multiple imputation for missing data. But there's clearly this distinction between the MEM and the LEM, which I hadn't thought about before, sort of fits into
Yeah,
a type of problem like that. It's sort of you're trying with your stuff. You're trying to sort of recognize that there's another phase that's been done, and you're
very complicated phase,
Yeah.
which is behind the firewall. I can't see it. And so I have a model outside the firewall, which is saying, oh, well, whatever happened in there, there was an outcome. And that outcome had a certain set of probabilities attached to it. So I have a model for that. It may or may not depend too much on what you did behind. Whatever dances you went through behind the firewall, it's not real interest to me.
You just need the error rate.
I just need the error rate.
And actually, the ONS produced, because they did work on their Beyond 2011, a very interesting strategies for stratified sample to get the error rates. They got a more efficient estimate of the error rate. I don't know if it's being used, but it was a nice paper. They
Yeah.
had
Well,
a more efficient post-stratified error rate.
Look, I think Jerry's really pointed out that in the past there was this some sort of belief that there was this holy church of data collection and unvarnished truth, what came out of there just with a set of weights attached. We know that's not true. Anybody who's been inside an agency knows there's all of this stuff going on in the kitchen, all right? And so when you see something coming out the other end, you can either take it as it is, or you can start to worry about how the preparation went, and try to build that into your inference. We now only have the tools. Now we're starting to have the tools. If you're Bayesian, you have MCMC tools. You can build models for all of these things and then simulate them out and see what happens.
Now,
Wonderful.
the MEM can be used to simulate.
That's what James does. That's what James is doing in his stuff, because he's sitting behind the firewall.
He's simulating this.
He's simulating the MEM and the ELE. He's doing them all. Yes.
Just to be fair, what happens inside the Survey Research Center at Michigan and NORC at the University of Chicago can be subjected to the same critique that Jerry just raised.
I got no problem with that.
not
Their
really a
organization.
critique, just a fact, a very, very, very hard problem that we have no idea how to.
Right, and it is generically applicable
Yes.
to the set of social scientists who take the published data as given.
Yeah, as wonderful. I mean, it's not. We know it isn't.
Or the set of astronomers. Just pick any discipline. The data go through something, but the raw data get pre-processed somehow before they get analyzed. And that, one of the things that with this verification server idea, in some ways it might extend beyond to lots of different parts of the process. So you can imagine a similar idea for the way an agency does missing data. So, people always say, well, how do I know that your missing data imputation model hasn't completely fouled up the analysis that I want to do? Which is a fair question because I don't know. But maybe we could create, these sorts of servers that have the complete data, and then you can run whatever model you want, do whatever imputations you want, and poke holes in the complete data some realistic way, which is hard, but then run whatever model you want, see how much the inferences change. Something maybe similar with record linkage.
It might be. I'm sorry, as you're describing that, I'm thinking of, is it Deep Thought in Hitchhiker's Guide? Oh, deep thought, here is what I've done. What do you think of it? Yes.
Right.
Okay, I think that's a nice ending for the morning session. So, keep thinking. So let's have lunch, and we are back, I think, in an hour for 2 more presentations, and then the wrap-up session. Thanks, Ray.
Thank you.